Hey everyone, and welcome. Today we're diving into a fun Leetcode problem called maximum candies you can get from boxes. It sounds a bit like a treasure hunt, and that's kind of what it is. We'll break it down step by step to make it super clear. So here's the gist. We have a bunch of boxes, some are open, some are closed. Each box has a certain number of candies. Some boxes might also contain keys to other boxes, and some might contain, well, more boxes. We start off with a list of boxes we initially have. Our goal is to collect the maximum number of candies possible. The main rules are, we can only get candies from a box if we can open it. If a box is closed, we need a key for that specific box to open it. And, of course, we can only interact with boxes we actually possess, either because we started with them or found them inside other boxes. Alright, let's walk through an example to see how this plays out. Imagine we have 4 boxes, numbered 0 to 3. The status array tells us box 0 is open, box 1 is closed, box 2 is open, and box 3 is closed. We also know how many candies are in each, what keys they might contain, and what other boxes they might hold. Critically, we start with only box 0 in our possession. So we have box 0, its status is 1, meaning it's open. We immediately grab the 7 candies from it. Nice start. Inside box 0 we also find box 1 and box 2. So now, we possess these boxes. Let's consider box 1. We possess it. But, its status is 0, meaning it's closed. Do we have a key for box 1? The problem description for this example shows that box 2 contains a key to box 1. But we haven't opened box 2 yet, so we don't have that key right now. So box 1 stays closed for the moment. How about box 2? We possess it, and its status is 1, so it's open. Fantastic. We collect 4 candies from box 2. And look, box 2 also contains a key for box 1. Aha! Now we have the key for box 1. This changes things. So let's revisit box 1. We have it. It was closed, but now we have the key. So we can open it. We get 5 candies. Inside box 1, we find box 3. So now we possess box 3. What about box 3? We possess it. Its status is 0, so it's closed. Do we have a key for box 3? If we look at our keys array from the input, no box gives us a key for box 3. So unfortunately, box 3 remains closed, and we can't get its 100 candies. That's a bit of a bummer. So what's our total? 7 candies from box 0, plus 4 from box 2, plus 5 from box 1. That adds up to 16 candies, and that matches the example output. You see how we had to keep track of what boxes we have, whether we can open them, and what keys we've collected. It's a dynamic process where finding one thing can unlock others. Okay, so how might we approach this problem in general? Our first instinct might be to just try to open boxes as soon as we get them. But, as we saw in the example, things can get a bit tricky. We might find a box, let's call it box A price, and it's closed. Then, sometime later maybe we open a completely different box, box B price, and inside box B price, we find a key for box A price. We need a way to remember that we have box A, and that we now have the ability to open it. This tells us that a simple, straightforward loop might not be enough. If the order in which we find keys and boxes matters a lot, we need a more organized system. So we need a systematic way to explore all the possibilities. Think of it like you're exploring a maze. When you find new paths or keys, you want to make a note and check them out thoroughly. A really good way to manage this kind of exploration is by using something called a queue. A queue is just a list where you add items to one end and take them off from the other, kind of like a waiting line. First one in is the first one out. This approach is a well-known technique called breadth first search, or BFS for short. Here's the idea. We'll put boxes that we can currently open into this queue. Then we'll take a box from the queue, process it, meaning collect its candies, find any new keys, and discover any new boxes inside. These new keys might allow us to open boxes we already have but couldn't open before. And new boxes we find, if they are already open or we have a key, will also be added to the queue. We'll need to carefully keep track of which boxes we currently possess, which keys we have available, and of course our running total of collected candies. To make this breadth-first search work smoothly, we'll need a few tools to help us keep track of everything. Let's imagine we have some arrays that store true or false values. These are called Boolean arrays. First, an array we can call CanOpen. This will tell us, for each box, whether we currently have the ability to open it. Initially, this will be true if a box's status is 1, meaning it's already open when we start. Second, an array called hasBox. This will tell us if we actually possess a particular box, either it was an initial box, or we found it inside another. Third, To avoid going in circles or opening the same box multiple times, we'll have a used box tracker. This will tell us if we've already processed a box, or if it's currently in our queue waiting to be processed. And finally, our queue. This is where we'll put the numbers, or labels, of boxes that we both has box and can open right now. These are the boxes, ready for us to explore. Alright, here's the Python code that brings this BFS idea to life. I know, seeing a block of code like this can sometimes feel a bit much at first glance, right? But don't you worry, we're going to walk through it, piece by piece, and explain what each part does in plain English. It's actually quite logical once we break it down. First up, we do some initial setup. We get nang, which is just the total number of boxes we're dealing with. Then, we create those Boolean tracker arrays we talked about. The hasBox array is initialized to all false, because at the very start we don't technically have any boxes yet, until we look at our initial set. The canOpen array gets its initial values from the status array given in the input. If a box's status is 1, it means it's already open, so canOpen for that box is true. Otherwise, it's false. The used box array also starts off with all false values, as we haven't processed any boxes yet. And finally, queue is initialized as an empty list. This list will serve as our queue. Next, we need to handle the initial boxes, the ones we're given at the very beginning. We loop through each box index in this initial boxes list. For every one of these boxes, we mark in our hasBox array that yes, we now possess this box. Then, we check two conditions. First, can we actually open this box? Is canOpen true for it? And second, have we already marked it as used box, meaning, is it already in our queue or processed? If both conditions are met, we can open it and haven't used it. Then we add this box index to our queue. And very importantly, we immediately mark used box as true for it. This used box flag helps ensure we don't add the same box to the queue multiple times if it's, say, open and in the initial list. Now we get to the heart of our BFS algorithm, the main loop. We start by initializing a variable. Let's call it collected candies to 0. This will keep our score. We also initialize a variable head to 0. Since we're using a Python list as a queue, head will act as a pointer to the front of our queue. The loop continues as long as head is less than the length of our queue. This condition basically means, are there still boxes in our queue waiting to be processed? As long as there are, we take the box at the head position. Let's call this the current box, and then we increment head. This is like taking an item off the front of the queue. Okay, so we've just pulled a current box from our queue. What's the first thing we do? Collect the treasure. We add the number of candies in this current box to our collected candies total. Next, we check if this current box contains any keys. We loop through all the keys found inside it. Each key for box is actually the index of another box. For each such key, we first update its status in our canOpen array to true, because we now have a key for it. This is an important step. If canOpen for this key for box was previously false, we've now unlocked it. Then comes a crucial check. If we has box for this key for box, meaning we possess it, maybe we found it earlier but it was locked, and we can open it, which we just ensured, or it was already open, and we haven't used box it yet, it's not already processed or in the queue, then we add this key for box to our queue for later processing. And, of course, we mark it as used box. This is how finding a key can lead to opening more boxes. After dealing with the keys, we look for any contained boxes inside our current box. We loop through each inner box we find. For every inner box, the first thing we do is update our hasBox array to true for this inner box, because we've now found it and possess it. Then, similar to how we handle keys, we check, can open this inner box? It might be initially open, or we might have found a key for it earlier. And, have we used box it yet? If we can open it and haven't used it, we add this inner box to our queue and immediately mark it as used box. This way, new boxes we discover get added to our exploration list if they're accessible. That's pretty much the whole loop. It continues to pull boxes from the queue, collect candies, process keys, and find new boxes, adding them to the queue if they're accessible and unprocessed. Eventually, the queue will become empty, meaning head will catch up to the length of queue. When that happens, the loop finishes. At this point, there are no more boxes we can open and process, so the very last step is to return the collected candies total. This will be the maximum number of candies we could get, following all the rules. So how efficient is this breadth-first search approach? It's pretty good. Let's talk about time complexity. In the worst case, we'll put each box into our queue at most once. When we process a box from the queue, we collect its candies. Then we iterate through any keys it contains, and then through any boxes it contains. So the total time taken will be roughly proportional to the number of boxes, let's call that nmes. Plus, we'll look at every key entry across all boxes, let's say the total number of these is k total. And we'll look at every contained box entry across all boxes, let's call that c total. So the time complexity is something like big O of n plus k total plus c total. Now for space. We're using a few arrays like hasBox, canOpen, and usedBox. Each of these will be about the size of n, the number of boxes. The QQ could also, in the worst case, hold up to n boxes. So the space complexity is primarily determined by these structures, making it big O of n. This is quite reasonable for this kind of problem. Alright, let's quickly recap the journey. We were faced with the maximum candies you can get from boxes problem. The core challenge was that our ability to get candies depended on a dynamic set of conditions: having a box, the box being open, or finding a key for a closed box, and finding new boxes within others. We saw that a breadth-first search, or BFS, is a really natural and effective way to handle this kind of exploration problem, where states change based on actions. The key to making the BFS work was diligently tracking several pieces of information: which boxes we has box for, meaning we possess them, which boxes we can open, either they started open or we found a key, and which boxes we've used box, to prevent redundant work and infinite loops. By systematically processing boxes from a queue and updating these states, we could make sure we explored all possible avenues and collected all the candies we were entitled to. And that's a wrap on this candy-filled adventure. I really hope this breakdown made the solution clearer and easier to understand. If it helped you out, I'd be super grateful if you'd hit that like button. Maybe even consider subscribing for more Leetcode explanations. And if you have any questions, or perhaps a different way you thought about solving this, please drop a comment below. I'd love to hear from you. And hey, if you're feeling extra generous, the Boba Fund is always appreciative. Keep on coding, keep learning, and I'll catch you in the next one.